Okay, you are live.
So, hey everybody, good morning, good afternoon, and good evening, depending on the time zone. This is Daniel, and this is the Zero Knowledge Learning Group, which is like a meetup series organized by, organized by the community and indirectly by Hyperledger or Linux Foundation Decentralized Trust. This is actually the third or almost the fourth series of this Zero Knowledge meetup series or learning group. And what we're gonna cover today is a theoretical concept of SNARK, of zero knowledge proofs, which is like interactive oracle proof. So, let me have just two slides on the logistics of the ZK learning group. So the idea is that we do this session every month. It's always the first Sunday throughout this year. So we started like somehow in January with like a kickoff meetup, and then we just have like one meetup each month. It always the third Thursday. It starts from 6 o'clock Central European time. It's like 9 o'clock, usually 9 o'clock Pacific, and I'm not quite sure. It's like 2 o'clock perhaps East Coast. I'm not so sure. The idea is basically, or the structure of the ZK learning group is that we have like always 1 hour, mostly a presentation and perhaps a short discussion. We're just gonna cover different topics, some zero knowledge proofs, mostly from programming and application developers' perspective, with some theory. And well, of course, these first three, the first three meetups, the first three sessions are more like theory oriented, but later on we just continue with development and application development. We got some coordination. The coordination, or the major element, major focus of the coordination is on Discord channel. So this is like the Discord channel. If you are not on the Linux Foundation Decentralized Trust Discord channel, you can basically just Google it. And if you just go to the Linux Foundation Decentralized Trust homepage, you will find basically an invitation to this Discord channel. And if you are a member in the Discord channel, then basically if you just scroll down, there's like a big tab which is like community or communities, and under communities you find like a zero knowledge learning group. And this is where the most of the discussion or material sharing and stuff like that happen. The reason is for that is because in 1 hour we don't have much time basically, and then for this reason I thought it's just best or it's just better to bring most of the discussion not off site, so not so much online, but in a way that we just don't necessarily be in like a call together for that. Of course, we're gonna have like meetups. You can find one meetup practically on meetup.com at the Linux Foundation Decentralized Trust meetup series. We got some repos as well, repository materials. It's at the moment in my repository, but it's gonna be like a lab under Linux Foundation Decentralized Trust. But you find the most up-to-date version at the moment under my GitHub repo. It's just again we're gonna progress with a decentralized Trust lab, so you will find all the zero knowledge materials there. And then we're gonna have some quizzes and small programming challenges at the end of each such meetup or session. And I hope there will be a possibility to get some merch at the end. Whoever manages these challenges as quizzes. I just own with like 1 or 2 quizzes, but again, I'm gonna do it just in a couple of weeks, and you will find everything under this chat, under the Zero Knowledge learning group chat, practically on the Discord channel. So the second one is again logistics. The second slide is again logistics. We started actually in February. I mean, officially, there were some kickoff in January on how to use like zero knowledge proofs in Hyperledger Fabric application development. But we started officially February with introduction from a theoretical parts with like definitions and building blocks. We continued in March with like polynomial commitments, more from a theory side. We're gonna continue today with theory, with interactive oracle proofs. The next 4 sessions are gonna be in May, June, July, and August, more like zero knowledge programming. We're gonna cover 2 programming frameworks or platforms and languages. One is SNARK, and probably the next one gonna be NOR. And we just do more like classical development and less theory. And from September, we're gonna focus on application development. So the idea is that we have just one big application area each month or at each meetup, at each session. So we can start with like off-chain transactions, then perhaps like proving solvency, proving funds and stuff like that. Then we can have like one application which is like rollup. It's like zero knowledge rollups, and then in December we can have some wrap up and some summary of applications, perhaps like how you can build like a zero knowledge virtual machine and stuff like that. This agenda is subject to change, and well, actually, if you have like a good topic, or if you are interested on a specific topic that we could cover like throughout this zero knowledge learning group, then just feel free to add like a comment like in this Discord channel, and then we can take a look if we manage. I mean, if I manage it from a competence and logistics side. I wouldn't say I know everything from zero knowledge or zero knowledge programming. Probably nobody knows actually. But again, so if you have like a specific wish which we should cover in this learning group, just feel free to share, and then I can take a look if I can manage it from a competence point of view. So that's like logistic, and let me just start with more like with the conceptual things, and that's the agenda for today. Again, I mean, this one gonna be still theory, so there will be like more like theoretical concepts without much application, without much programming. But I promise basically this is gonna be almost the last meetup or session on this theoretical part. So we're gonna start with some summary or wrap up of the previous 2 events. So I have just one slide on SNARK or ZK SNARK, of course, elements of building a SNARK. Then I have a slide on interactive oracle proofs, then some building blocks. Then we're gonna cover Plonk, and we're gonna cover Plonk more in details. So Plonk is like a zero knowledge. It's actually an interactive oracle proof, but basically it's like a whole ZK proof system. So we're gonna cover Plonk more in details, like how you can build computational trace, how you can construct polynomials with some summary, and at the end I have some literature and links and some Q&A. So that's the plan for today. I mean, it's gonna be more like a presentation. So if there's like any issues with my connections, or if you don't understand anything, I mean, just feel free to jump in and mention, or just feel free to mention in the chat. But otherwise, it's more like a presentation from my side, and then we can have like a bigger Q&A and discussion at the end. I think it's gonna be like 30 minutes altogether, I guess. So I hope we're gonna have some time at the end for Q&A and for discussions. So let's start with SNARK, with ZK SNARK. So what's a ZK SNARK? It's a succinct non-interactive argument of knowledge. Usually we got like two roles. Again, this is like summary. It's like a brief wrap up of the previous sessions. Usually we got a prover and we got a verifier, and the prover tries to prove that she knows something for the verifier in a so-called succinct way. Succinct means small proof and fast to verify practically. And it might be like zero knowledge as well. So the prover might prove something that she knows without actually revealing the fact that to be proved. So the whole field is a little bit tricky. If we want to prove something, we usually program the domain in a way. So if there's a problem which should be proved, usually we just write a program on that. But due to the mathematical complexity, we usually consider something specific as a programmed task. So we usually don't, I mean, we start sometimes with a high-level language, but basically, if we speak of like computation, what we mean is more like an arithmetic circuit for the first one. So computation model is pretty specific. It's like a circuit which has like two input variables. One is a public input, that's a so-called X public input. The other one is W, it's like a private input, or we can call as witness, and it evaluates to a value basically. Or there are like computation models that basically the arithmetic circuits evaluates to zero. It's more like a predicate interpretation and not a function interpretation of the arithmetic circuit, but these two representations are actually equivalent. So this is like a middle layer of computational model. And again, so usually we start from high level computation, we just translate it to arithmetic circuits. And at the end, we gonna transfer everything to polynomials. And the mathematical properties of these polynomials gonna give us practically the properties of SNARK or ZK SNARK. So basically, there's like a pretty big theory behind which is based on polynomials. We have usually two algorithms. One is a prover. The prover gonna use the public input, the private input, and there might be one further step which is like kind of a pre-processing this whole computation. So based on these two items, the prover gonna create a proof, and the verifier gonna use the public input. The verifier not gonna use the witness, not gonna use the private input, but gonna use the proof, and there might be some pre-processing as well. And then based on these three parameters, the verifier either accepts or rejects this kind of a proof. And then there are some properties which is like succinct. Succinct means small and fast to verify, so small as a proof size and fast to verify as a computational time. Complete means that like if there's a proof which is correct, then the verifier gonna accept it with a very high probability. Then there's zero knowledge property, which means that that's the other direction practically. So if the verifier accepts something, that there should be basically a proof, or the prover actually really knows a fact that is proved, and then, or at least with very high probability. And there's one more property, which is, well, actually an optional property. You might not need it in all of the use cases, which is zero knowledgeness. And zero knowledge means that basically this whole protocol reveals nothing from the private input, from the witness, from the fact that should not be revealed. So that's like small summary of SNARK. And then basically there are many ways of doing a SNARK, but building a SNARK, but the most general model has like three parts. One part is the so-called polynomial commitment, or one building block is the so-called polynomial commitment. That's what we covered last time. The second part is the so-called interactive oracle proof. And there's like a third part or third building block. The third building block is the Fiat-Shamir transformation. The Fiat-Shamir transformation makes an interactive proof a non-interactive in special situations. So basically, if you're just wondering what's interactive proof and what's non-interactive, well, basically we got a prover and we got a verifier, And if there's like many interactions, so like prover sends something to the verifier sends something back, and there's again some more communication, and the third round of communication between prover and verifier. That's a so-called interactive proof. And then if there's just something which you can present from the prover and the verifier accepts or rejects, that's like a non-interactive proof. And then, of course, I mean, especially in blockchain applications, we like the non-interactive proofs because that's what you can publish on a blockchain. And then if you publish on the blockchain, everybody can verify it, all the validators or all the users practically. Otherwise, if your proof is interactive, it's more difficult. It might not be used so well in blockchain applications. But again, the fiat Shamir practically creates an interactive proof to non-interactive in special situation. I mean, of course, if there's like a random value from the verifier, which is chosen randomly and sent back to the prover, basically. So what we covered last time, that was like functional commitments. And then functional commitment on a high level means that we have a function, or we have a polynomial basically. And what we do basically is that the prover chooses basically a function from this F function family. Okay, we speak of like functions and polynomials, but you can imagine that these functions and polynomials are actually representations of some kind of a computational model, or some kind of a computation. And basically, this computation describes a specific problem that you want to basically use in your zero-knowledge proof. So again, the prover chooses one function from a function family and then commits this function to the verifier with a commitment. And basically what the verifier does, the verifier can open this committed function in one point, and then the prover can basically prove or gets the value or sends back the value of this one point to the verifier, and then with a proof that this is really a point of this committed function, and the function is really in the function family. And of course, this can be in zero knowledge, so basically without revealing the function itself. So this is like a general scheme again. So a functional commitment or a polynomial commitment is practically committing a function from the prover to the verifier, and then basically opening it at one point. That's what a functional commitment, or that's what a polynomial commitment does. And if it looks that way, we get one function, we can commit this function to the verifier, and then basically the verifier can ask the prover to open this function, this polynomial, in one point. This is like point x. And what the prover does, sends back basically y. So y equals f of x, basically. So that's the value of this committed function. And there's basically a proof. And the proof basically is a kind of a proof, or cryptographic proof, which says that this y is really an evaluation of x in terms of function f, in terms of the committed function, and f is really in the committed function, and f is in the function family practically. So that's what a functional commitment. And then what we're gonna do is that today is that we're just gonna extend this functional commitment a little bit, and this extension is the interactive oracle proof. So interactive oracle proof is a similar algorithm, something similar. What we're gonna do first, we have our computational model. So we're gonna prove that we got this C circuit, but it's a computational model which have two inputs like X and W, and then X is the public input and W is basically the witness, is a secret input, and then it evaluates to 0. So instead of having this computational model, what we use is that we use different functions, But again, I mean, these functions gonna be somehow transferred from this computational model. So we got a few functions. This is f0, f1, and fn. And well, I mean, this is an extension of functional commitments or polynomial commitments. So basically, the prover gonna commit these functions to the verifier, and then basically in a sequence, and basically at the end, the verifier can ask to evaluate this function in a certain point or in certain points. Okay, so the prover gonna have like a few functions, and the interactive oracle proof has like two parts. First, there are like a few repeated steps. So first, the prover gonna send one function to the verifier. Actually, the prover doesn't send a function itself. Instead, it sends practically a commitment of this f1 function. And then the verifier sends back basically a random parameter to the prover. And then the prover sends the second function to the verifier. Again, not the function is going to be sent, but basically a commitment to this function, a functional commitment to this function, and so on and so forth. So at the end, the verifier sends back some random parameter, and then based on this random parameter, there's going to be like one last function, which is sent from the prover to the verifier. And that's like the first step. And this, we don't need this last R if I'm not mistaken. Yep, so we wouldn't need this one. So this is like repeated steps. We're gonna just repeat n times, just sending the n functions from the prover to the verifier. And we're gonna have like one final step, which is verification. Verification means that basically the verifier has all the functions that were sent from the prover to the verifier. And again, these are not the functions, but basically the commitment of these functions. And basically in the verification step, the verifier can open basically these functions at certain point and actually knows the public input as well. And that opening at certain points basically can evaluate that basically these functions are evaluated at a certain point and then evaluated to 0, supposing that basically this computational model was expressed by these functions. So that's actually interactive oracle proof. It's very high level, and I would say I'm actually not a mathematician, so it is kind of a non-mathematical summary of interactive proofs. Basically, I would say it extends the functional commitment to something way more complicated or having way more round from one function or one polynomial to several polynomial evaluations. And of course, this is like a SNARK itself as well, so we can speak of like completeness, knowledge soundness, and zero knowledge property of such an interactive oracle proof. I'm gonna cover one such interactive oracle proof more in depth. So we're gonna take a look, we can take a look more in details in the following slides. But just having some building blocks, we already started last time. There are some useful gadgets or basically building blocks that we can use and that we can take a look. So for instance, one of the easiest one is a test, is testing if a polynomial is 0. So it looks that way. It's actually it itself is more like an interactive oracle proof as well. But basically it looks that way that if we want to test if a polynomial is 0, what we can do is basically pick a number or pick actually an input of this function, and then check if that function is 0 itself. So if you just basically pick a random point of a function, of a polynomial, then if that's 0, then with very high probability, the whole polynomial is 0 as well. And the reason is for that, that a classical polynomial with like d degree, that means that it has like d roots. And if we have like a p domain, which is pretty big, then basically the probability that we that we pick a point that evaluates to 0, and the whole polynomial is non-zero, it's very, very small. So basically, this is a very easy test. We committed the function. We just send back one x item, one input item, and basically, if the prover sends back the evaluation of this function at point x, and this evaluation is 0, then we can conclude with very high probability that the whole function, the whole committed polynomial is 0 as well. So it is surprising, but it's a very useful gadget. And then we can just extend to take a look like if two polynomials are equal. Because if you get like two polynomials, then if they are equal, then basically like one polynomial minus minus another polynomial equals to 0 as well. So we can just put back, or we can just use the zero test polynomial to check if two polynomials are equal. So we can do it in a way. If we just commit two functions, two polynomials, again, it's getting to be more in a more interactive oracle proof side, to be more interactive oracle proof kind. But if you just commit like two polynomials, so you can imagine the first step is like committing like f, and the second step is like committing g. That's like the first two steps, something similar as we mentioned here. But if you have if you committed f and if you just committed g, what the verifier should do to check if the two committed polynomials are really equal or not is to ask the prover to evaluate these two polynomials at a randomly chosen point. Okay, and if in a randomly chosen point, these two polynomials evaluate to, evaluated to the same value. So if fr at random point or fx equals gx at random point, then we can conclude that the two polynomials are equal in a very high probability. So it's like pretty tricky, but basically not so complicated to see it. And with similar building blocks, we can just basically build up some more structures, like what's used in Plonk very heavily to test is if a polynomial is 0 on a set, which is like a set of values, so it's just not one value. So we don't test if the whole polynomial is a 0 polynomial, but we just test if the polynomial is 0 on a set of values. And we can have like some check. We just prove that that certain input values, the sum of certain input values equals to a committed polynomial to a given value, and we can have something to production check as well, where the input values evaluate to a committed polynomial to a given value, and then we prove that the production of the input values basically evaluates to this committed polynomial to a given committed value practically. Okay, so this is just building blocks, and let me just see more in details how intuitively looks like. Again, I'm not gonna go like very much deep into the mathematical details, but well, sometimes I would say this is like deep enough. So what we're gonna take a look that's like one explicit construction of constructing basically an interactive oracle proof with a polynomial commitment scheme. And we just didn't mention we got like these two major building blocks, like again polynomial commitments and interactive oracle proofs, and there are just different versions both for polynomial commitments and interactive oracle and IOPs as well. And you can just combine them. So based on these combinations, you can have like many different proof systems. It's practically, so usually cryptographers say, cryptography is more like a zoo with many different animals. So in a sense, like ZK snarks and SNARK and STARK, that's also a zoo with many different animals, and you can find, or you can get like most of these animals simply by using different polynomial commitment schemes with different IOPs. Okay, so but this is one version, and this is what we call as Plonk. And Plonk looks that way. It has like many elements, many transformations. So I'm just gonna cover these transformations step by step. So first, again, we think of this model. We got like a computation, which is a circuit, which has an input, which is public, and a private input, and it evaluates to 0. So it's more like a predicate. And what we have here basically is an arithmetic circuit. So we got like inputs, and we got like addition and multiplications, and this is just the simplest use case, but we can make it, of course, more complicated, like having more inputs, either private or public inputs, and like having here more like addition and multiplications. So the first step is that we create from this arithmetic circuit something which is a computational trace. And you can think of computational trace first. We can have this arithmetic circuit in an abstract way without any values. But for a certain evaluation, we can just put in numbers practically. So this is like an evaluation. This is like an X public input. This is like a W private input. This is like just an addition gate, and this is just an output. So if you just put in like numbers, we get like 1 and 8, and there's gonna be like 9 at the output. So having this arithmetic circuit with an exact evaluation, we can create a computational trace. And the computational trace is practically a table. As the first row, we're gonna have the inputs. So this is like input 1, this is like input 2, but we might just well have like several other inputs as well. So these are just the inputs. And as next rows, we're gonna have the gates. So we got like gate 0. We have just one gate here, but we might as well have like several gates as well. So this is just gate 0, gate 1, gate 2, and so on and so forth. And what we have for each gate, we get just a number. So this is like the left input of the gate, this is the right input of the gate, and this is just the output of the gate. It's 1, 8, and 9. Again, we have just one gate, but I just listed like several other gates as well. So supposing we have like a gate 1, again, we would have here like an input, a left input, we would have like a right input, and we would have like an output as well. And if you have like gate 2 as well, gate 2 has like left input, right input, and output as well. Okay, and then basically we have something which is an output of the circuit. If we have the gates, the output of the circuit is basically like the output of the circuit, like the output of the last gate. Actually, it's a bad example in this sense because we would need like that the output is 0. Again, this is 9 at the moment, but I mean, if I have just a more complicated structure, then we could have like 0. So that should be just 0. Again, we just want to use it in a predicate form, so this should be evaluated to 0. But just consider this that this example is just part of a bigger example. If we have like here some other variables as well, that would like we could consider that the output would be 0. Okay, so in a Plonk, what we're gonna do first, we have of course, we have somewhere one complex program describing our domain. We're gonna just construct somehow our arithmetic circuit model, and as a first step for an explicit evaluation of the arithmetic circuit, we're just gonna create a computational trace, and computational trace is just a table having the inputs and having all the gates as inputs and output values, basically. So as a next step, we're gonna cover, or we're gonna construct based on our computational trace something which is polynomial. And then we can have polynomials in several ways, but basically what we use in Plonk is that we're gonna encode all of the inputs and all of the gates to polynomials. So we're gonna encode inputs in a way that like p w to the minus I equals I for all I input. So basically, it's like saying values for a specific point for this, or that's like a way of setting specific points for the inputs of a polynomial. So in this example, we have the point that pw to the minus 1 equals 1, pw to the minus 2 equals 8, and these are like two specific points of the polynomial, and that's for the inputs. But of course, if we have like here, I don't know, three more inputs, like the number third input is like, I don't know, 9, then we could say that pw to the minus 3 is like 9. It's like one more point to the polynomial. And we're gonna encode all of the gates as well. So these are the gates, these are not the wires, these are the gates as well. And we're gonna encode the gates to points of polynomials in a way that we say that the polynomial w to the 3l, that's l is like the numbers of that gate, that equals like the left input of the gate, the pw to the 3l plus 1 is the right input of the gate, and the pw to the 3l plus 2 is the output of the gate. So in this sense, or in this example, we have just one gate, basically gate 0. It's again, it's a very artificial example, or you might as well consider it's just part of a bigger example. So basically, what we do here is like pw to the 0 equals 1, because that's the left gate. We just have like pw w to the 1 equals 8, because that's the right gate, and we have like pw to the 2 equals 9, because that's the output of this gate null. But if you have like more gates, the logic is pretty much the same. So like having the gate number 1, it's like L is like the number of the gate, or we can consider as number of the gate. So pw to the 3 equals the left input of the gate, pw to the 4 equals the right input of the gate, and pw to the 5 equals the output of the gate. And if we have like gate number 2, then again it looks that way, that pw to the 6 equals the left input, pw to the 7 equals the right input, and pw to the 8, if I can correct correctly, that's like an output. Okay, what's important perhaps, this is like, I mean, specific points of a polynomial. So we usually don't really like using specific points or defining a polynomial with specific points. We usually like more like having a polynomial with like in a coefficient form. But basically you can transform coefficients or the coefficient polynomial form based on these exact evaluation points with the help of, for instance, with the help of a fast Fourier transformation. So it's basically doable, even if that's like looks a little bit tricky. We can create, based on this form, with the help of fast Fourier transformation, the classical polynomial coefficient form. Okay, so that's number 2. And then now what we should do, basically, I mean, we have like all the steps, all the transformation steps. Again, the transformation steps, we have a high-level model. From our high-level model, we just create like a computational or a lower-level computational model, which is an arithmetic circuit. Based on our arithmetic circuit, for an explicit evaluation, we can create something which is a computational trace. Based on our computational trace, we can specify exact points of our polynomial, and based on our polynomial, we can basically create like a classical coefficient form of our polynomial. So basically, what we have here, we just created from our high-level domain problem or functional description of our problem, we just created basically a polynomial. And what we need to do, we just need to create somehow the SNARK proof, the zero-knowledge proof, with the help of our computational model, which is already the polynomial itself. So the question is, how do we do it? We got the prover. We gonna just commit this polynomial again, which is already actually our whole computation. And the way we prove that that's our problem and that's our computation is that we prove like four things. The first one is what we're gonna prove is that our inputs are correct. So again, we get like a complex polynomial at the moment, but we need to prove somehow that our inputs are really the inputs that we just specified. That's step number one. Then we need to prove that basically our gates were evaluated correctly in this polynomial, again, in this crazy polynomial, which means that we need to prove that we get like sum and multiplication gates. That's number two. We just need to prove that the wiring is correct. I mean, the wiring means we have just one plus gate here, but if we have like a multiplication gate on top, then basically the output of this sum gate, of this addition gate, is basically the input of the multiplication gate. So that's like wiring, and we should prove that the wiring is correct. And basically, at the end, we should prove that the output gate is 0. Again, it's like not the best example, but basically for the first round, we just consider like computational models which are more like predicates, so they evaluate to 0. Okay, and if we just prove somehow these four things for our polynomial commitment, then basically we're done. So that's then we have our SNARK, then we have our zero knowledge proof. So how do we do it on a very high level? If we consider proving that the output is 0, that's the easiest one, because it looks that way, that basically the output is the output of our last gate, that should be 0. So it's enough to prove that basically the last gate evaluates to 0. And then you can do it like with very simple functional commitment, just opening the committed polynomial at a certain point, and this certain point should be the w to the 3l plus 2. So basically this output, which is like, again, this output, which is like the last output. And if you just ask the prover to open with the help of a polynomial commitment this last output, then practically we have a proof that basically our polynomial evaluates in the last gate to 0. So that's the easiest one. The rest three, I mean, are more complicated. We usually use for further proofs something which is another polynomial. So we're gonna create some helping polynomials or helping functions. So for correcting inputs, we're gonna need like to create one polynomial which encodes all inputs again to this computational model, and we call it as an input polynomial, if I'm not mistaken. And as soon as we created this V help polynomial, which again encodes all the inputs, then we can use like the zero test or one specific zero test as a useful gadget to prove that like P minus V equals 0. So practically with this help V function, polynomial, we can prove that all of the inputs were encoded correctly. Okay, so these are like the inputs. We just create one help polynomial which encodes all of these inputs, and we just create in a way, that basically it's just PW minus 1 equals 1, PW minus 2 equals 2, if I'm not mistaken, and that's all. So we don't have the rest of the functions, and basically if we have like one polynomial which encodes only these input parameters, and then we can have basically the full polynomial that we created based on the full computational trace, then we can use the zero test in a special way to prove that practically all inputs were encoded correctly in our committed polynomial. So that's number one. The next step is proving the correctness of the gates. Proving correctness of the gates means basically that in our committed polynomial we just encoded plus for a certain gate and multiplication for another certain gate. It is realized by having a special help polynomial, which is a selection polynomial, and it's pretty simple. Basically, it looks that way. We just have this selector polynomial, one at certain point, usually like w to the 3l, if that's an addition gate, and we can have like 0 if that's a multiplication gate. And basically combining this selector polynomial with our committed polynomial and then using the zero test in a special way proves basically that all of the gates were encoded in a correct way in our full computational model, which is practically a full computational polynomial. And there's a third one as well, which is proving the wiring. So again, if you think of like wiring is that you got an output of like an addition gate, which is like an input of another gate. So if you just take a look on the computational trace, you can already see it. So this is like input, and input is basically the input of gate 0. Then we can imagine that this is like another input of our computational model, and that's basically an input again for gate 0. And we have something which is an output of this gate, and we have just one gate in our computational model. But again, if you just imagine that basically we would have like another gate, then basically the output of this gate should be here like the left input, for instance, or the right input. And then you can imagine if you have like more gates, then the output is basically like an input of another gate. So that's what wiring basically. And proving that our computational model, which is like the whole constructed polynomial, encodes basically this wiring in a correct way. For this, we just create one more polynomial, which is like a wiring polynomial. It's a little bit more tricky. It just rotates somehow the coefficients, and then basically, if it's done, then again with the help of like a special zero test, it can be proved that basically all the wiring were evaluated or were encoded in a correct way. Okay, and then that's the whole idea. Again, it was actually for a mathematician, it was very high level. For a software developer, it was probably low level enough. But generally, that's the summary. I mean, that's the whole idea. Well, perhaps I would mention just two things. First, there are like steps here which are not dependent on the exact computation, on the exact trace. So if you just compute the wiring polynomials or the selector polynomials, they are just independent basically. They are just independent from the exact input and output values, from the exact computational trace. So basically, computing like the wiring or selector polynomials can be done in a preprocessing step as well. Okay, so if we have like preprocessing, then usually what we do is we just compute these wiring and selector polynomials. But nevertheless, what we do, we just start with our like high-level computational model. We just decompose it or compile it somehow to an arithmetic circuit, and based on this arithmetic circuit, we can just, for a certain evaluation, we can create like a computational trace, and then based on this computational trace, we can build a polynomial. We can specify the exact evaluation of these polynomials, and with the help of a fast Fourier transformation, we can even create like the coefficients of these polynomials. And then as soon as we have the polynomial, we can just commit our full polynomial from the prover and the verifier. And then what we can do is that we can just prove that we committed a polynomial that really encodes our exact problem in a way that we prove that the inputs are correct, we just prove that the gates are correct, we just prove that the wiring is correct, and we just prove that the output is 0, basically. And as it is basically in this sense more like an interactive proof, so we just have several steps. Of course, at the end we can use the Fiat-Shamir transformation to make it non-interactive. So again, on the one hand, it was pretty much high level for the mathematical complexity. On the other hand, for a computer engineer, it was pretty low level. But I'm gonna have some literatures and links at the end, so you can take a look more in details if you feel like. One thing that I would mention perhaps is that one idea of Plonk. So we usually say that arithmetic circuit uses like additions and multiplications, but if we have these Plonk constructions, just based on this table representation, it can be easily extended with other gates as well, which makes like the whole proof and proof system more efficient. So usually we can have like lookups and stuff like that. If you imagine in a proof system, we usually have like standard tasks, so like proving a signature of an elliptic curve or having an elliptic curve operations or stuff like that. So building up everything from scratch with the help of plus and multiplication gates is pretty complex. But Plonk has the advantage that you can just extend this computational trace, this arithmetic circuit with extra gates, with custom gates, and these custom gates might make like certain specific task actually more efficient. So that was basically the theoretical part for today. I still don't have quiz. I promised the quiz for the polynomial commitment part as well. I'm still not. I'm gonna have the last quiz and probably this quiz as well somehow next week. I will post both of these quizzes actually in the Discord channel, so you can take a look. And then I would say that was our last theoretical session or meetup. I just shared some links, resources, and literatures. It has some basic ideas of interactive oracle proofs, but basically you can find like all the deep dive math and mathematical elements as well in some of these links and literatures. So again, that was as my plan. That was the last theoretical session and meetup, and from next month we're just gonna do more programming. We're just gonna start with Circum, and we continue with Noir. So that was my presentation. It was taking longer than I expected, as usual. So if you have like any questions, yeah, just feel free to unmute yourself or just use the chat as you wish. Yeah, just go ahead. Yeah.
Are you a buyer? I'm Alfred. Mortgage broker, owner of Island, golf course in Hawaii Point. The first
Yep.
Can be like, we can be partnership from the that Tesla and BYD.
Yeah, I'm not quite sure if I understand the question. Your voice is a little bit like jumping, or at least for me. So can you just put into the chat, and then I can take a look and then answer it surely. It was just the network is not necessarily the best. Nevertheless, I'm just asking the questions in the chat in the meantime. So basically, first question, if you get like the I mean the present. Sorry.
Can you afford to sign a non-disclosure fee?
Sorry, I don't have the question. So in the meantime, I'm just reading the questions in the chat. So the first question, if you get like the presentation, so the presentation gonna be shared basically with Linux Foundation Decentralized Trust. I'm gonna put everything basically into this Discord channel as well. So you will find everything there. You will find the presentation, and you will find basically the recording as well. So you will find basically everything. Yeah, again, one question for the slides again. The slides gonna be posted in this for the first one in this Discord channel. As a second one, I think David gonna probably send you an email as well. So if you just actually on Meetup, or if you joined via Meetup, I would say probably the slides gonna be sent to you on email as well. So I'm just reading one of the questions. It seems like more complicated for me for the first one on mortgage broker, car dealer. I'm not so sure if I have the question based on this. But anyway, if you have like any more, I would say technical question in terms of like zero knowledge proofs, and then feel free to ask. So if there's no more question, then I would like to thank you very much for your attention. And then, well, we're gonna continue in 1 month with Circum development, and otherwise, well, happy holidays.
Hey, Daniel, is still out there?